chapter 18 starts by defining what is a spontaneous process. Y'all, a spontaneous process is a process that will occur under a certain set of conditions. Will ice melt? Under certain conditions, yeah. So if we were to consider in this room an ice cube sitting on a desk, then we know that that H2O solid would become H2O liquid. That would be spontaneous in this room. Could that water, after it's melted, could it refreeze in this room? If we didn't change any of the conditions, could it refreeze? No, it could not refreeze. So the idea of water in this room freezing, that's not spontaneous. That's not going to happen unless we do something different. Okay? So a spontaneous process is one that occurs under a certain set of conditions. If we look at this picture, this is a good picture that's used to show a spontaneous process and a non-spontaneous process.
You said water refreezing in this class is not spontaneous?
Correct.
Okay.
Because what you have in A is a glass bulb that's full of a gas. And this valve is closed. When I open this valve, what's going to happen? The gas is going to fill both containers. That's a spontaneous process, isn't it? We all know that would happen just by common sense. I don't need any kind of thermodynamic law to tell me that if I have gases and they're separated and I open the containers, we know gases will fill the containers. Is this a reversible process? Could I take it back to A? In order for it to be a reversible process, then whatever I did to make it go from A to B, open the valve, if I close the valve, will it return to A? No. So in order for it to be reversible, I have to do the opposite of what I did to get it there. Do you understand what I'm saying? So if I close the valve, this gas is not going to go back and fill A. So this is a spontaneous process. Spontaneous processes have one direction. So in other words, if it's an equilibrium process, equilibrium processes are not spontaneous. They are not classified as spontaneous. Why? Because equilibrium processes, isn't it going forwards and backwards? It's going both directions. And so spontaneous processes only have one direction. Could, in this example, could I make B? Could I get it back to A? Well, yeah, I could somehow force all this gas back over here and then close the valve again, right? But I wouldn't have taken the same path to get it to return back to its original state. You know, it's just like we talked about that ice cube in the room. The ice cube on the desk is going to melt. In this room, that water is not going to refreeze unless I take the temperature down below freezing. So I would have had to have changed one of the conditions to get the process to reverse. Typically, a negative delta H is a spontaneous process. Because negative delta H means it's getting rid of energy. And so that can be a spontaneous process. And a lot of times, if the delta H is positive, we call that not spontaneous. This is just chicken scratch. But that's not the only thing we consider. Because y'all, in order for ice to melt, it's got to take heat in to melt, doesn't it? Ice melting would feel cold. Isn't ice melting positive delta H? And yet we just said that's a spontaneous process. So enthalpy, H, is not the only thermodynamic term thermodynamic measurement that we can use to tell if a process is spontaneous or not. There's got to be something else to consider. That something else that we need to consider is called entropy. Entropy is a measure of disorder, or sometimes it's referred to as a measure of randomness. The symbol for entropy is a capital S. S is entropy. Yes, we will look at delta S as well, because y'all know the delta means change. Yes. What I did when we were going back over enthalpy and everything we knew about it, I didn't remind you guys of the units. Do y'all remember what your units are for energy? Joules and kilojoules. Okay. Enthalpy, y'all, most of the time it's going to be given in kilojoules. Entropy, most of the time, is going to be in joules, because entropy changes are really small, so we report those changes in terms of joules instead of kilojoules. So you'll have to watch for that, because you don't want to compare kilojoules and joules, because the numbers don't exactly match up. Just like the sign of delta H tells us whether, like if it's negative up here, that tells us exothermic, and the positive delta H tells us endothermic. Well, the sign of S tells us whether it's more disordered or more ordered. Okay? If S is positive, that means we're moving towards disorder. If S is negative, that means we're becoming ordered. A positive S moving towards disorder can mean it's spontaneous. A negative S, things moving towards order, is not spontaneous. And I'm not going to introduce it right now, but in a minute, we're going to talk about the second law of thermodynamics and how it relates to that. But that's where we're headed with this. I'm going to tell you some things you can look at to just qualitatively tell if we're getting more ordered or more disordered. And then we're going to look at quantitative, okay? Just numbers, calculating S. So first, let's look at qualitatively measuring S. And let me explain to you what you'll need to do. I think I have a... Yeah. What's that? You can, yeah. This is the table that I'm going to use to explain qualitatively the values of S. In your book, there's a table on page 782. It's different from this one, y'all, but you can use either table to kind of point out what's happening. For starters, this table is broken down into gases and liquids and solids. Okay? If S is a measure of disorder, does it make sense to you that if you have a gas, and y'all know gas molecules are constantly moving around, right? Does it make sense to y'all that a gas would have more disorder than a liquid? And then even further, a liquid would have more disorder than a solid? If we just think on a molecular level of what's happening to the molecules, solids are very ordered, and then etc. Okay, you can kind of see that from this table. The top part lists gases. Look at their entropy values, relatively speaking. Okay, then in the middle you've got liquids, and at the bottom you have solids. So can y'all see that these are bigger, and then, relatively speaking, gets a little lower and a little lower. And yet, it depends on what you're comparing. Okay, so that's one thing we can consider. Another thing we can look at is if we're comparing compounds that are similar. For example, hydrogen, nitrogen, and oxygen, the first three gases on this table. Hydrogen has an entropy, it says, of 130. Nitrogen is 191. Oxygen is 205. Would you guys agree with me that hydrogen, nitrogen, and oxygen, I mean, they're similar, right? They're all three gases. They're all three diatomic, so we could compare those. Why do you think oxygen is more disordered, has a higher entropy than nitrogen, which is more disordered, has a higher entropy than hydrogen? What do you think it could tie back to? Not that. Good guess. It's even simpler. You can't compare like two things that aren't the same. You wouldn't compare like water and benzene, C6H6, because H2O and C6H6, they're not the same. It needs to be kind of the same chemicals. It's not on here, but guys, if you were to look at the noble gases, those are all similar. Yeah, it's just helium and neon and argon, etc. The further down you go, the heavier they get. Therefore, they increase entropy the further down you go. So the higher the molar mass, it'll have more entropy if they're similar chemicals. Let's step this up a little bit, because that's one thing to just look at a substance and say, what would nitrogen's entropy be compared to oxygen? But what if we're looking at across a chemical reaction? Is entropy increasing or decreasing? So if I gave you this, calcium carbonate, when it's heated, y'all, it will break down into calcium oxide, and it'll give off carbon dioxide gas. And that's the balanced equation for that process. Calcium carbonate yields calcium oxide and carbon dioxide gas. Keep in mind, if S is positive, that's moving towards disorder. If S is negative, it's moving towards order. If I start with just calcium carbonate, and then I heat it, and when I'm finished, I've got calcium oxide and CO2 gas, do you think it's become more disordered? Why? Because it made a gas. So does it make sense to you that since I produced a gas, and gases are more disordered than solids, that I predict this equation would have a positive delta S?
I think gases are more
disordered.
So you're telling me if that would have broken down to two solids, it would have been a negative?
No. You would not have been, if it had been two solids, you would not have been able to predict it qualitatively. You would have had to calculate it. Okay? So, the delta S of the system, what is the system? It's what we're interested in measuring, y'all. It's the calcium carbonate and the calcium oxide and the CO2. The delta S of this system is positive. Let me give you another equation, and let's see if we can guess what we think will happen. Nitrogen gas plus hydrogen gas makes ammonia. All right, I've got a gas and a gas making a gas. So I can't, it's not as easy as that first one, right? That first one was, oh, that's no problem. I'm making a gas and I started with a solid. I've got to increase the delta S. How many moles of reactant are there?
4.
4, right? Because I've got 1 nitrogen, 3 hydrogens. I've got a total of 4 moles of gaseous reactants. How many moles of products do I have? 2. Does that make sense to you that that would get more ordered? If I went from 4 moles of a gas to 2 moles of a gas, it's more ordered. So what would the sign of delta S of this system be? Negative, because I'm getting ordered. How do we calculate the entropy change of the system? We've already looked at it and said, okay, it ought to be positive. But how do I come up with an actual number? Remember in Chem 1 when we looked at that appendix in the back of the book, Appendix 2? There's an appendix in the back of your book that lists standard enthalpy changes for compounds. It also lists entropy changes. Guys, we use Appendix 2. So find that in the back of your book. We're going to use that formula to calculate the delta S for this reaction. How am I going to do that? I'm going to go to Appendix 2. I'm going to find calcium carbonate solid, and I'm going to write down under calcium carbonate what the entropy is for it. So guys, I'll look those numbers up in Appendix 2. And y'all would have access to Appendix 2, or I typically write them on your test. The S values are this. Then what do? I take each one and I multiply it by its coefficient. And yes, I'm going to write it on here just so you can remember that you've got to multiply it by its coefficient. Just so happens that this equation is 1, 1, and 1. Then what do? After I multiply them by their coefficient, do you remember? Add up the products, add up the reactants, and say products minus reactants. And that will give you the entropy. So y'all calculate that. So when we add up the products, add up the reactants, and then subtract them, you should get 160.5 joules per Kelvin mole. That's the units of entropy.